Hello, everyone, and welcome to the Applied AI Seminar Series. Today, I'm going to be talking about semi-supervised image labeling with vector embeddings. Let me begin with a brief intro to image embeddings. We can utilize image embeddings such as CLIP, which stands for Contrastive Language Image Pre-training, as a way of embedding images within a reduced vector space. We can also associate textual representations with these images as well, and these can be stored in a unified embedding space. So the unified embedding space maps images and text into a shared space, positioning semantically similar items closer together. We can utilize cosine similarity to compare CLIP embeddings, identifying the most semantically similar items efficiently. We can also store these embeddings in vector DBs for scalable high-performance similarity searches. It's a very versatile tool which enables zero-shot classification, content-based filtering, and multimodal AI systems by linking visual and textual information. I would like to now talk about PCA and how it can be used for feature decomposition. We can utilize PCA as a statistical technique for dimensionality reduction of large data sets. It identifies principal components, which are the directions of maximum variance in a data set. We can transform data into a new coordinate system based on these components, where the first principal component captures the most variance, the second captures the second most, etc. This allows for data compression by keeping only the top n components. It's extremely useful for visualization, noise reduction, and feature extraction in machine learning. I would also now like to introduce k-means for semi-supervised labeling. Within k-means, we can apply an initial clustering where we can utilize k-means to read in and label a data set which is labeled or unlabeled, utilizing features like CLIP embeddings. We can then take these labels which have been learned via k-means and we can propagate them. So we can assign the majority label from labeled points to all points within the cluster, effectively propagating labels to the unlabeled data. We can also apply a confidence threshold where we set a confidence threshold based on a cluster purity or distance from the cluster centroid. We can then propagate the label to the unlabeled points exceeding this threshold. We can refine this iteratively as well, utilizing newly labeled data to retrain a supervised model, and then recluster and repeat the process, gradually improving classification accuracy. Active learning is also possible with k-means. We can identify uncertain points near cluster boundaries for human labeling, focusing the manual effort where it's most impactful. We can also utilize ensemble-based approaches where we combine k-means with other semi-supervised methods, such as label spreading or self-training for more robust results, resulting in which is especially useful in complex data sets like medical imaging. So now I would like to show a demonstration of a model which is utilizing CLIP embeddings to visualize and automatically label a complex data set comprising data which is representative of a chest X-ray data set, which contains images which are related to cases of pneumonia and non-pneumonia. So in this data set, which I'm running, or in this code, which I'm running on the Center for High Performance Computing GPU cluster, I'm installing some necessary packages, downloading and extracting the data set, importing some required libraries, setting up the device and loading the CLIP model. So here I'm specifying that we want to use the GPU if it's available. Otherwise, let's use the CPU. I'm loading the CLIP model, which we're pulling from this installation of the OpenAI CLIP package. And then we define a custom data set, load the images, generate the CLIP embeddings. This takes about 5 minutes on a A100 system. It takes much longer on a local laptop or in Google Colab. It's much faster on our GPU-based systems at the CHPC. We can then take these CLIP embeddings, which were generated for all of the X-ray images, and we can perform PCA and visualize. Here, I'm projecting to the two components which have the most variance, and basically reducing this to a 2D problem. I'm plotting the cases of pneumonia versus non-pneumonia here from the vector embeddings, and we can see that there's some degree of overlap in this 2D PCA space between the two data sets. We can also visualize this as a 3D PCA, and we can see similarly that there is a high degree of overlap within the data as in some regions. We can also see how many PCA components are necessary to explain most of the variance within the data. We can determine the explained variance ratios for an increasing number of components. The clip embedding is 512 components. And we see from our analysis that you can explain 95% of the variance with 111 principal components. With the 2D PCA, we're visualizing about a quarter of the variance. With the 3D PCA, we're visualizing about a third of the variance. The clip embedding is sufficient for capturing the total variance of the data set. We can go further and utilize k-means to determine the optimal number of clusters within the data set. Doing that, we determine via the elbow method and silhouette method that the optimal number of clusters within this data set is 28. With 28 clusters, we can optimally label the data set. And here we have a visualization of those clusters where we have labeled them accordingly, and we can see that these represent unique distributions of data within the data set. And if we look at the composition of the clusters, whether they contain pneumonia versus non-pneumonia, we can see that the clusters segregate towards one classification over the other. So this is a unique way of generating unique classes of data within the data set. So it's a very powerful tool. This code will be available on our GitHub repo and will be available to run on the CHPC. We can now utilize those clip embeddings to also train multimodal deep learning models. So we can utilize various data types such as image, text, and genomic data within the context of healthcare to generate richer insights. So this would offer improved diagnostic accuracy and prediction robustness over unimodal methods by leveraging the complementary nature of different data types. These applications range from enhanced diagnostics to precise treatment planning and continuous patient monitoring. We can also use the clip embeddings to train transformers. So transformer models excel in healthcare by analyzing multimodal data without sequential processing constraints. They effectively handle healthcare data types, improving upon RNNs and CNNs, and they utilize self-attention mechanisms to capture complex data dependencies, enhancing multimodal analysis. They're also somewhat interpretable, which means that they benefit healthcare decision-making, offering transparency and patient care analysis. Transformers are very versatile, allowing them to be a promising tool for integrating diverse healthcare data, aiming to improve patient outcomes. We can take those clip embeddings and we can also store them within a vector database. So a vector database is extremely useful in terms of allowing for efficient similarity searches, where we can enable efficient similarity search by indexing high dimensional vectors, allowing quick retrieval of semantically similar items. It's also very scalable. So vector DBs are designed to handle large scale data sets, making them suitable for managing and querying extensive collections of clip embeddings generated from diverse and voluminous data sources. They can also be used for context-based image retrieval by finding or serving relevant images or text based on the input clip embedding. So this is a very efficient way of searching for similar patients based on their imaging or a textual representation. It's also very integral with AI pipelines. So vector DBs seamlessly integrate with AI pipelines, enhancing the performance of tasks like recommendation systems, visual search engines, and multimodal AI applications that rely on embeddings. So in summary, you can utilize vector embeddings as a feature representation mechanism, such as CLIP, to convert raw data like images into high dimensional feature vectors capturing semantic information. They can be used with PCA to reduce the dimensionality of the embeddings, retaining most of the important features while reducing noise and computational complexity. We can also utilize k-means clustering with the PCA reduced embeddings to propagate labels from the labeled data points to unlabeled points within the same cluster based on the cluster purity or distance metrics. In addition, we can use the newly labeled data to train a classifier, then use this classifier to refine cluster assignments and label propagation. We can repeat this process to improve labeling accuracy. We can also utilize some level of uncertainty sampling by identifying data points near cluster boundaries with low confidence scores for manual labeling, effectively combining active learning with the semi-supervised approach. And within the context of vector embeddings, we can utilize CLIP to map images and text into a shared space for classification and filtering, supported by scalable vector DBs for similarity searches. So these are all the basis of extremely powerful tools that we can help you develop further within the RCIF CHPC. I'm very happy to support users who are interested in utilizing these codes on our systems, and I would ask that you reach out to us, either myself or Scott Johnson, to help you get started on your journey of utilizing embeddings within the context of your own research. Thank you. My name is Dennis Trujillo, and I appreciate your time. Thank you. Bye.